Welcome back to my series on programming in assembly language on the 8-bit computer using the Max65 assembler editor cartridge. If you're feeling a little sense of deja vu right now, of all the mistakes I've made in my amateurish YouTube career, this was probably the worst. I deleted the video that I spent over 2 hours making last night, 80 minutes to record it and then another to listen back and catch all the mistakes I made. And I didn't have a backup, so here I am, I'm recording it all over again. Now, if you have watched that video that I deleted, I promise I'm not covering anything new in this video. There's one thing I'm going to shift around to a different place, but everything I covered in that previous video, nothing new is going to be added to this video, and everything I covered there, I'm going to try to cover again here. So I'm going to assume that if you are listening or watching past this point in the video, you didn't see the first one, or you just want to see it again, hopefully with less mistakes than what I made last night. So let me say that too. I always listen to these before I post them up on YouTube. If I find any mistakes in them, I will put them in a pinned comment right under the video. So if you're watching the video and like 20 minutes in, I say something stupid, look to see if I didn't catch it in the comments before you let me know about it. And also, last thing, thank you. I hit 500 subscribers today, which is pretty cool. Didn't expect that to ever happen. So up until now, we've been covering a joystick program on how to, a demo on how to read the joystick using various methods and some code optimization and so forth. And I know everyone's probably as sick of that program as I am, especially since I'm re-recording the video. But there are two more things I want to cover on it, and then we're on to all new stuff, good stuff. We're going to talk about graphics, we're going to talk about color, we're going to talk about input-output control blocks, and starting to lay the foundation for a game demo that we're going to write in assembly. So all that stuff's coming up after we have one last pass at the joystick reading thing, which we won't bring back for a couple videos until we need to read the joystick again. So the last one we left off with is this one here, where we are using AND to mask out the bits to see if they're turned off, because if the first bit's turned off, then the stick's being pushed up. If the second bit's turned off, then the stick's being pushed down. And we said, oh, when you do AND with the value of stick in the accumulator, that changes the value in the accumulator. So if the stick wasn't pressed up and I came down here, the accumulator's been changed by this AND, so I need to get the stick value again, and so that's why we're using variables in the last video. And this here is a way to do a temporary variable to transfer the accumulator into the X register and then transfer X back into the accumulator. And there's one other way you can do this in a temporary thing. Let's say your X registers and Y registers were tied up with something else. You could also push the value of the accumulator onto the stack, and then if the stick wasn't being pressed up, then we can pull the value of the accumulator back off the stack to get the original value of stick 0. And our program starts at 5024. Go to DDT. And I'm going to pull down on the joystick right now as I start stepping through this with the Option key. So you see here a D, which is 13. I'm going to get these right tonight. 13, C is 12, B is 11. I'm going to get these all right tonight for once. Anyway, this is the value of D in the accumulator. Before I do the and rec it up, I'm going to push this D onto the stack. Here is the stack pointer. It's at FF right now. So when I execute this command, you see the stack pointer change to FE. The stack is a location in memory that goes in page 1, which means it occupies memory locations from 100 to 1FF. And you can think of it like the plates at the Chinese buffet when they put out some clean plates. Putting something on the stack is like putting another plate on top, and then that pushes the plate below it down, and so forth. So right now I push this into 1FF, and then the stack pointer went down to 1FE. So if I go to 1FF, you can see that's where my 13 went. It's stored on the stack right now. And if I look up at 1FE, the plate there is AB. So just remember that. And then we're going to go back to 5028, I believe. Right. So now we have 13 in the accumulator. We're going to AND 13 is 8, 4, and 1. So when I AND it with 1, 1 and 1 is going to be 1, so it will not set the 0 flag. So you see this got changed to 1, but the 0 flag didn't get set. So no 0 flag, this will not be true, so it's going to go down. It's going to pull the value off of the accumulator. So this goes to 13, back to 13. The stack pointer goes from FE to FF. And if I go look at 1FF, you remember the AB that got pushed to FE is now back in FF. Now, that all works fine, except you have to be even more careful with the stack than you do with the using the XY registers. And here's why. Let's say I'm running this program that keeps looping around like it was, and I'm continually pushing up on the stick. So what would happen is I'm going to come in here, I'm going to push like a 14 onto the stack, and then it's going to be a 0. It's going to branch to stick up. Then I come down through the loop. I come back up here. Then I get a new value. I'm still pushing up. It pushes the value on the stack again, goes to here, branches down to stick up, and so forth. So if you notice what's happening is I'm pushing as long as the stick is up, but I'm never doing any pulling. So what can happen is you can totally mess up the stack, and a lot of the computer routines are using the stack. So you have to, whenever you stick anything in the stack or pull anything off the stack, you have to be super careful to leave it the way you found it. So the way to fix this is here. If I go to stick up and I know I'm going to skip this, then where I do the stick up at 330 and 350, I can add a line in here to pull from the stack. So now I load in stick 0, I push it onto the stack. If it's a stick up, it goes down to stick up, loads the X register, then it pulls that value back off, leaving the stack the way I found it at 1FF. So this time we'll do sum. And we'll go to DDT. Now I'm pushing up on the stick. This value is 14, so it's 8 and 4 is 12 and 2 is 14, and there's a 0 here. So when I AND it with a 1 and a 0 is going to be 0. That's going to flip the 0 flag to 1, which will make this execute and drop down to 5039. So watch, when I push it on the stack, it changes the address to FE. I do the AND, I do the branch to stick up, I load the X register, and then I pull that value off the stack. I don't really care about doing anything with it. I just want to leave the stack the way I found it. So that's the thing you have to be careful with if you're going to use a stack to temporarily hold variables, is to make sure you don't miss cleaning it up, because you can easily crash the computer that way. All right, so the last thing about the joystick program is, I believe it was Brian, not Carl, as I said in the first time I recorded this video, who said, so originally, the whole reason we're using a variable, right, is because the AND is a sort of destructive thing that changes the value in the accumulator, so we wanted to store it, so after the AND destroyed it, we could get it back again and check it if we had to. And he said, well, there's also the bit command, which does the same thing as AND, except it only affects the 0 flag. It doesn't change the value in the accumulator. And that sort of sounds like a good thing. Well, then I don't have to store any variables, because I can do that bit comparison. It does the masking the same way, and then I don't have to worry about storing the value in the accumulator somewhere, because it never changes. The problem with that is the bit operator does not support immediate mode like this. So I can't say bit 1 and bit 2. All it supports is absolute mode and 0 page mode, which means it will only work with a single memory address. It doesn't even support absolute X or absolute Y, just absolute or 0 page. That's the only thing it supports. So to make it work with bit, you'd have to do something like this. So what I've done is created some literal values that'll be in memory. So this will be a memory location called is stick up. This one is stick down, because that's what these are for, with the 1 and the 2. Then I don't need this. And this would look like this. So now it's, what it's going to do is it's going to go to this memory location. It sees there's a 1 there, do the bit 1 with this, and so forth. Nobody really uses the bit command, because this whole thing is very awkward. I mean, right now, it's okay, I'm only comparing 2 values. But if I wanted to compare 4 or 15 or 20 values, right, then have to locate memory locations, and just, it doesn't give you any flexibility. So nobody actually uses a bit command really, but it does work. Let's assemble that. I'll just show you it in action. Now note, because I added these 2 bytes in memory of 1 and 2, my start got shifted by 2 bytes to 5026. And I'm going to pull down on the joystick. And so there's a 13 in there. And now what this does is say bit and then location 5024. So 5024 is holding a 1 in it. So it's going to do a bit with the 1. And because this is a 1 here, a 1 and a 1 is a 1, it's not going to set the 0 flag. But it also doesn't change the value in the accumulator. Whereas when I do it with 2, this is 842, there's a 1 here, and I'm sorry, there's a 0 here, and I AND it with the 1, then it's going to flip the 0 flag when I do this bit comparison. So the 0 flag flipped, this still never changed, and now I'm going to go and print stick down, blah, blah, blah. So that's how the bit command works. It's, like I said, it's kind of awkward, so we're really not going to use that. So in the video so far, before we get on to the new stuff about graphics, we've covered the AND operator, we've covered rotate right, we've covered logical shift right, arithmetic shift left, and rotate left. We've carried all those bit instructions. So there's and bit now. Tonight is bit. So there's 2 more I want to cover and just show you how they work. Originally, this was in another part of the video that I recorded yesterday, but I'm moving it here to put all the bit operations together. So let's say I had the joystick pushed down, which is 8 and 4 and 1, 13. If I AND that, right, with 1, if I AND this with a 1, I'm going to get if I AND this with 2, remember, both of them have to be 1. This sets the Z flag. That's what happens with AND. Now there's an operation which is called OR. It's so this instruction is OR. And how that works is when I have bits, it says if either bit is a 1, then the result is a 1. So in this case, if I ANDed these 2 bits or these 2 bytes together, this would come out with 0, 0, 0. One of these is a 1, one of these is a 1, one of these is a 1, one of these is a 1. So that's how the OR flag works. So basically what it does is if the AND flag masks out all the bits except the one you want, or mushes them together into one thing. So, and again, if I had done, and obviously this is not the Z flag because there is not 0 as a result. If I did an OR with 1, then as you can see, it basically mushes them together. Mushes 2 bytes together. So AND does the masking, OR does mushing them together, and the other one is exclusive OR. And how that works is if both bits are 0 or both bits are 1, So in this case, they're both 0. I get a 0. This one of these is a 0 and one of these is a 1, so it stays 1. One of these is a 0, one is a 1, stays 1. And because these are both the same, because these are both the same, so 2 zeros is the same as 2 1s is the same as 2 zeros. So exclusive OR says only set the bits where the values are different. If they're the same in the 2 bytes, and you might say, well, what is that used for? Well, what that's used for is toggling bits. So let's say this is my original is 13, and I do an exclusive OR. So what the exclusive OR says, hey, if this bit was, if I set these 2 bits to 1 with the exclusive OR, then this is going to be a 1 because they're different, and this is going to be a 0 because they're the same. So what you can see, and let's just to clarify. So what that means is, with the exclusive OR, for every bit I set, it toggles the original bit to its opposite 1. So in this case, when I have a 0, it changed it to a 1. And when I have a 1, it changes it to a 0. So what you use exclusive OR for is to toggle certain bits. So let's say I wanted to have a character and I wanted to make it an inverse character. I can EOR it with, the high bit set. And then what I would get is what I would get is this. This stays 1. So anything that's a 0 stays what it was, and the 1 will toggle it to the opposite. So in this case, I took the original value and I just toggled the high bit so I could change it into an inverse character. So we have AND, masks bits. We have bit, which does the same thing but doesn't change the value in the accumulator, but doesn't support any mode except absolute mode. And then we have OR, which says if either bit is set, then set the result. So that's used to mush bits together. Usually you'll have a high bit and a low bit, and you'll mush them together to make one number again. And exclusive OR is used to toggle bits. And that's all we're going to talk about for logical operators. Now we're on to the good stuff. We're going to start talking about graphics. So when I was doing my action series, I basically started it the same way. So I started with showing people how to read the joystick. Then I showed them how to move, create a graphics 1 screen and move a character around on the graphics 1 screen using a joystick. Then we showed how to redefine characters so that character on the screen looked like my dog, and we could move my dog around the screen using the joystick. And then later we got into Antic Mode 4 and 5, which let me add colors to my dog. And then we got into a custom display list and all that other stuff. But it all started with a demo program I'm going to show you. I'm using my Ultimate card tonight, so I can show you the okay, and I'm not going to go over this code. You can go watch an action video. I'm just going to show you how it works. So what we're going to be trying to do in assembly language. Helps if you compile it first. So this is what it does, right? But right, if you would say, okay, you can teach me how to do this in assembly language? Yes, that's what we're going for. And eventually we'll redefine this to look like something, and we'll redefine the joystick trigger so it does something on the screen when we press it, and all kinds of good stuff. I also I suffer for this channel. Not only do I re-record an hour-long video again a night later, but I also wrote a program in BASIC, so I really am pulling out all the stops here. I think I said last night, I don't think I've actually written a program in BASIC in 20 years, maybe more. And the only, I did actually write this in Atari Basic Revision C, you know, that comes on the cartridge. The only reason I'm using Basic XL here is because I like how it helps if I load it. So this is the basic program. If I run it, it's a little faster in Basic XL than Revision C Basic, but the idea is the same. So this basic program. So what we're going to do is try to now here's the neat thing about either the basic program or the action program. This I'm showing because I'm assuming most people have more knowledge of basic than they do of action. So what I want to point out here is other than these 5 statements in here, graphics 17, SetColor, color 62, and plot. So graphics, SetColor, color, and plot. Other than those statements in this program, everything else that's in here, you could write right now in assembly language based on the previous videos. So just with that information alone, you have enough tools that you could write this. I mean, I'm going to show you how to write it, but you could write it yourself if you had these characters, so or these basic commands in assembly language. So that's what we're going to work on. Tonight we're just going to do how to write the basic graphics command and the action graphics command, same thing, in assembly language, and we're going to show how to write SetColor in assembly language. And eventually we'll get to this, but it's not going to be tonight. So now the only reason I'm loading this joystick program one more time is because I'm stealing some part of it for our new program or our new demo. So what I want to do is the purpose of the demo tonight is we're going to learn how to open a graphics 1 screen in assembly language, and we're going to learn how to set the background color to green, like we saw in that previous screen. And then we're going to go to an infinite loop so it stays on the screen and we can look at it until I press the joystick button. So we're going to steal this part here where we do this infinite loop. And instead of jumping back to start, we're going to jump to... So we're just going to do an infinite loop here until the trigger is pressed. And so I want to keep I want to get rid of all the lines up into 380, so I'm going to do this. And I'm going to get rid of 700 to 780. So all that's left in memory is this. That's it. And I'm actually going to change this to end, because it's really, yeah. So I'm going to change this to end. All right, so that's our infinite loop. And we're going to renumber this, I don't know, like way out there so I can write code underneath it. So okay, so now I have my infinite loop. Now we're going to start writing a brand new program. And last night, what I did was this, and I got problems. So tonight, I'm going to remember that I wanted to start at hex 4000. I'm not going to forget that. And here, when you're doing things for the first time, comment this out so when you're doing your first assembles, it won't assemble to memory in case you mess something up, like, for instance, starting this without the, starting it without the $sign. All right. Now we're going to start defining a bunch of variables and system equates that we're going to need to do the graphics operations and the SetColor and all that stuff. So we're going to talk about these all one by one. But the first thing I want to set up is the stuff that I use to end the program, that infinite loop that I have. So that would be string 0. That's not new, right? But I'm going to add a new one now. So I usually like to have my programs exit on either the joystick trigger being pushed or the start key being pushed. So reading the start key happens, the values of pressing the start key are held at a place called console, and trust me on this one, it's DO1F, okay? And then I'm going to be looking for the console to be, the start key to be pressed, and the value of the start key is 6, all right? And actually, then I can go, I'm going to go here. And after 210, I'm going to add some new code to check the console key. So at let's say 2012, rush, I'm going to load console. What's the value in console right now? And then I'm going to compare that to the value of 6. So what this is going to do is take the value that's in that memory location where start is pointing to and compare that to the start key being pushed. And if that comes out 0, which means they're equal, then I'm going to branch if equal to end. And then let's see how that looks. So now this is my new ending routine. It says, is the joystick trigger pushed? Then branch to the end. Then look at the console key. Is the start key being pushed? Then branch to the end. Otherwise, just keep looping around here until one of those two things happens. Now I'm going to go to, I'm going to assemble this. And I didn't get any errors, so I'm going to go back to the beginning, right? And we're going to, oh, where's my 120? Of course, it didn't go to memory. Maybe I didn't hit enter. That's a common mistake I guess I make. Change some line and don't hit enter. So now I'm going to assemble this. So here's something else I talked about, and the start of this start is not where my program starts, right? So let's look at this assembly. I know I was using start all along, but I think from now on, what I'm going to be doing is starting my program with begin and end. So begin and end, because I want to use start here. So start is not going to be where my program starts anymore. Begin is going to be where my program begins. Now, I don't have this called begin right now because we're going to do that in a minute when we write the real part of this program. All right, so the thing I want to know is my program actually starts at 4001. So go to DDT and, right, I can see here, this says load the accumulator with the value of trigger 0. If it's 0, branch down there to exit. Otherwise, load the value out of the console location. Compare it to the value in 4000. So if I look here, the value in 4000 is a 6. Compare it to the value in 4000. This is absolute addressing, right? And then branch if equal to the end, otherwise loop around. Now, what I've been doing in the past is to run my programs, I have been exiting to DOS and running at a memory address, and I've run into issues with that. I didn't know why I blanked on this, but you can run your programs from DDT by using the G command and giving it the starting address of your program. So in this case, I can just say start running at 4001. And now nothing is happening right now, right? Because I'm in an infinite loop. But I do expect if I press this trigger that it's going to go back to Max 65. Or back to DDT, I'm sorry. So it goes back to DDT, and then I'm out, right? So I know my infinite loop works. I'm just going to try the start key now. Go 4001. You'll just have to trust me that I'm pressing the start key right now. All right, so I know my infinite loop part works. All right, time to add some more things. The next thing we're going to add are our equates for handling the all the color stuff. So color 0 is the color register for register 0 for color 0. So if in the SetColor where I do 0, 0, 0, the first 0 is, this color register. And we're also going to need this for the plot command is column cursor and row cursor. And let's go to good old mapping the Atari, right? So row cursor is the current graphics or text screen cursor row. And column cursor is the current graphics or text mode cursor column. So we'll use that in the plot command to set the row and the column when we're doing plots. Now, I want to talk about something with the color 0 command. And that is what you're going to see a lot tonight is a lot of use of the addressing mode called absolute X, which is where we take a memory address and we index it by the value of X and in the X register. Now, you've seen this before in our Hello World demo where we index into the string of characters using the X. By changing X, we would advance along the memory locations in the strings. How your Atari sets up a lot of values in memory is like this. So there's color 0, 1, 2, 3, and 4. There's player color 0, 1, 2, 3. There's paddles, 0 through 7. Stick, stick 0 through 3. Triggers 0 through 4, and so forth. There's a lot of places where, multiple things that do the same thing are right after each other, referenced with a number. And rather than in my equates having to define every one of these as a separate thing, color 0, color 1, color 2, color 3, color 4, and having 5 different equates in here, I can use the absolute X addressing to get to the color that I really want. So, for instance, if I said load the X with 4, and then I did store whatever's in the accumulator, some color that I want to change the color to, I can say color 0, comma X. And what that means is it's not really going in color register 0, it's going into color register 0 plus 4, so it's going into color register 4. And we use this a lot in Atari, and we're going to use it a lot when we get to the next bunch of equates that we're going to do. And let me get rid of this. And the last things that we're going to need for our graphics stuff is we're going to declare a variable to hold the luminance to hold the hue for SetColor, and a variable to hold the luminance for SetColor. And if you remember from the previous video, this stands for data space or data storage, whatever you want to call it. It just says reserve 1 byte in memory. I'm going to use this to hold some values. It's basically a variable. Sorry, need a drink. I'm doing 2 videos in 2 nights. All right. Now, the next piece is crucial to almost all the rest of the stuff we're going to do, is we're going to start talking about the IOCB, which stands for Input Output Control Block. Now, the Input Output Control Block is one of the greatest things about the Atari design, because what it does is there's a bunch of subroutines already built into your Atari operating system. That's basically how it runs, right? Everything even you see on the screen is being put there by some operating routine that's already written in machine language in the ROMs in your computer. And what the input control block functionality lets us do is it gives us a block of 16 bytes that we can fill with various values and then hand it off to an operating system subroutine, which will carry out our commands for that device. Now, your Atari supports built-in many devices already. So like K for keyboard, D for disk drive, C for cassette, P for printer, S for screen, which is what we're going to be using tonight. It handles E for editor, which is like a combination of the keyboard and the screen, and R device for the RS-232. And if you're using a Fujinet, there's an N device. And the reason there's an N device is you're not limited to the devices that are in the computer that it already knows about. You can write your own devices as long as you write the routines for the central input-output vector to control. So the next thing we're going to add is the address of the actual subroutine, which is called the central input-output vector. And what that is it's a subroutine. And after we set up some values in an input-output control block, we're going to call this subroutine with those input control block filled in with some values, and it's going to do stuff for us. So let's talk about the input-output control block. There are 8 of them. They start with input control block 0 to input-output control block 7. So there's 8 of them. And you can see, well, maybe you can't see, but you're going to take my word for it. It takes 16 bytes, so from 340 to 34F. And IOCB1 adds 1 to that 4, so it goes 350 to 35F. ICB2 adds another 1 to this middle digit, so it's 360 to 36F. So this is another case where I don't want to write out the bytes for every one of these control blocks in my equates. What I want to do is write them once and then get to the channel I want. These are also called channels, right? Open channel 1 to the graphics or keyboard or whatever. I can get to the channel I want by using that X addressing. So I'll show you how that works. So there are 16 bytes in the input-output control block. And we only need to do the basic graphics command. All we need are 5 of those 16. That's all we need. So we need this one. This is IC COM. COM means command. So what we're going to put in this is the command that we want to send to the IOCB to do something for us. So for instance, if I put a 3 in there, it's going to open the channel. If I put a C in there, it's going to close the channel, right? And if the other thing I want to do tonight is put a character on the screen, so that would be a B. So these are the, and there's other ones, right? Rename, erase, protect, all the different ones you can put in there. So this byte is used to tell the IOCB subroutine what I want it to do for me. These 2 bytes make up a 2-byte address. And this address can mean point to different things. But this is the, basically this is the input controlled buffer address, low byte. And this is a buffer address, high byte. for the screen tonight, and let's just make sure I got these. And this one is for you, Nick Felino. I'm going to put all right, what this does is this says I'm going to put 3 bytes into memory, the S, the colon for screen, and 9B is the Atari carriage return. So, you know, when we did our Hello World program, we didn't use a carriage return. We just counted how many characters were in there, and when we got to the number, we stopped. But the input-output control block routine will read your buffer until it gets to this. So we don't have to tell it how many bytes are in the, the screen name. We can just, as long as we end it with a carriage return, it'll read the S and know that we mean the screen. So I'm putting the data at the end, as someone once suggested. Okay, so let's go up here. We have 2 more that we're going to need for the IOCB control block. And that is 2 auxiliary bytes. Auxiliary byte 1 and auxiliary byte 2. Now these are very specific bytes. So this is the command. This is the address of the data we wanted to read. In this case, we wanted to read the device name screen. And these bytes are different depending on if I was using the screen device, or if I was using the FujiNet end device, or if I was sending it to the printer. These could have different values. So we're just going to talk about the ones that we need for opening a graphics screen tonight. We're not going to care about the other ones quite yet. And we're going to also, just to make our code more readable, we're going to define the 3 commands that we're going to use with this IC command byte. We're going to use the open command, which is, as I said before, that's 3. The close command, which is C, which is 12. Sorry, emphasis mine. And then the other one that we are not going to get to tonight, but I'm putting it in here now so I don't have to put it in later, is to put a character on the screen, is 0B. All right. And now we are ready to start doing some stuff. So as I said, I'm going to start my programs now with begin and end. Okay, so we want to open a channel to the screen in Graphics 1 mode without a text window. So if you looked in the demo program I ran before in Action and Basic, it was a Graphics 1 screen. It did not have the text window, and it was a full screen. So that's what we're going to do. We're going to open we're going to use the open command to the screen to open it in Graphics 1. Now, this is actually a technique. I was looking through a bunch of Atari assembler books that is really not covered, except in, I only found it in one obscure book from Byte Books, and even that had a typo in it and some extraneous logic that wasn't needed. But even like Atari Roots, which I consider to be the best book on Atari assembly language, does not teach you how to open the graphics command with the IOCB. Well, he does all his graphics screens building custom display lists. And we're going to get to that. We're going to build custom display lists. And in fact, when we get to Antic Mode 4 or 5 with the multicolored characters, that's not available as a graphics mode that I can call through IOCB. So I have to write a custom display list to go to the Antic chip directly. But really, there's, and I haven't read every issue of Compute, Antic, and Analog in a long time, so I don't know if somebody covered it somewhere else. But the thing I'm about to show you tonight, opening a Graphics 1 screen, I don't think has been, it's certainly underrepresented. And what are the advantages versus doing a custom display list? The reason most people don't do it the way I'm doing it tonight is, in assembly language, you want as much control over everything as possible. And creating your own custom display list lets you decide where the screen is going in memory. It lets you decide exactly how your screen looks, and you can handle all those things. And we're not at that point in this series of tutorials to start allocating memory. So for the demo that we want to do, it's fine for us to just call the already built-in subroutine that's already there for us to open a Graphics 1 screen, and the computer's operating system is going to take care of all this stuff that we would have to do manually in assembly language, like allocating memory for the screen, creating the Graphics 1 display list, pointing the character sets to the right place. The operating system does all that for us by using this method. So one method, creating your custom display list like in Atari Roots, gives you a lot more control. This method is probably better for beginners because the operating system handles the heavy lifting till we're ready to learn that. So I know there's other ways. I'm just saying this is why we're going to learn it this way for now. All right. Before you open a channel to the screen, you have to close it first because the screen's usually open, right? If you try to open a screen that's already open, you're going to get an error. On the other hand, if you try to close a screen that's already closed, you won't get an error. So it's always okay to close the screen first because closing an already closed screen won't give you an error. So the first thing we have to do is now what I'm doing is I'm loading the X register with 60. So if I go back here to IOCB 0, and that's at 3-4, right? That's what I have here, the 3 4s. But then I add 6 to it with this into absolute X mode. 6 and 4 is 10, which is A. So 3A0, that's going to get me IOCB 6, which is the graphic statement opens channel 6. So we want to use channel 6. And so first we're going to tell and the other thing this does is when I call this subroutine, the operating system subroutine, it looks in the X register to see which channel you want to open. So that's how it knows when I say close this or open that, it's going to know exactly what channel I want to open or close. So first we load the X register with 60. We're going to load accumulator with the value close, right, which is C. We're going to store that in. So what that says is take this address 342 and add 60 to it, so it's going to get 3A2. So it's going to store the close at 3A2. And for the close, that's all I need. I just need to say, hey, channel 6, close it. Done. That's all there is to the close. Now we get to the open. I try to keep these at 6 characters or less. Same thing, I always have to load that X register because I jumped to a system subroutine here. I don't know what the X register is when I come back from that subroutine, so I can't take a chance that it still has a 6 in it, so I'm going to always load that X register with 6 again. Now I'm going to load in the open command, which is 3, into the accumulator and store it at the comma X. So again, it says do this, but for channel 6, not channel 0. Now we need to fill in the buffer address low and high. So what we're going to do is load the accumulator with the value, not of the value of, don't load it. So this is immediate mode, which says, I don't want you to load this with the value that's stored in screen. What I want you to do is load it with the address of screen. And this here, this less than sign, is Max65's way of saying, give me the low bit of screen. Or the low byte of screen. And then we're going to store that at be a low, again, X offset by X, 60, so I make sure I'm doing the right one. And you use the greater than to get the high. So let's just see if this assembles. We're not going to try to run it right now, but I just want to show you. Oh, I have... oh, I put 2 spaces on my labels. That's... All right, so our screen is at 4034, right? 4034 is our screen. So the low byte is 34 and the high byte is 40. 34 and 40. So now when I assemble this, you can say load the accumulator with the low byte of 4034. You see, load the accumulator with 34. And here I say load the accumulator with the high byte of 4034, and that's where the 40 is. So it is taking the address of that screen and and putting it into the buffer address for us. All right, now here's where we have to put the values in the auxiliary bytes. And the best place I've seen for this is out of the Atari Technical Reference Manual, page 57, Atari Technical Reference Manual, where it says when you're doing an open to the screen, the device name is S, we got that. And the handler supports the following options. In auxiliary byte 1, there's these 4 bits that can be set. So the C bit says if I put a 1 there, it's not going to clear the screen when I do open the mode. So I don't want that, so I'm not going to set that bit. The S equals 1 indicates set up a split screen with text and graphics in modes 1 through 8. And I don't want that, so I'm not going to set that bit either. I do want read and write because I want to write characters to the screen and I want to read characters from the screen later when I do a locate. So I do want these 2 bits. So that's the 8-bit and the 4-bit. So that equals 12. So what I want to put in auxiliary 1 is 12. If I wanted a split text screen, so let's say I wanted to do graphics 1 on top and I wanted to put like high score and player, high score, current score, player lives remaining in a text screen at the bottom, I would put a 1 in this bit, the 16-bit. So I'm either usually going to send a 12 for read-write or 28 if I want the text window. In this case, I want... I just want the graphics 1 with no text window. So I want read-write, which is those 2 bits. That goes in auxiliary byte 1, again, indexed by X. In auxiliary byte 2, the only thing matters is the low 4 bytes, and that is the screen mode 0 through 11. Note that if you open a graphic screen 0, it doesn't matter what you set these 2 bits in the auxiliary byte 1, it just ignores them. But in this case, I want to open a graphics 1 screen. So I'm just going to say I'm going to load this with 1. And that's really all I need to open a graphics 1 screen. I have my command bit that says open. I have this address to the screen handler name in the buffer address, low and high, and I have the byte that says do read write in auxiliary 1, and I have the say that says graphics mode 1 in auxiliary 2. So now I can just jump to the subroutine and it will open the graphics 1 screen. Now I would run that right now, but all you would get is a black screen, so you wouldn't really know wouldn't know that it was running. So we're going to do the SetColor first, and then we'll run it. So you should see a graphics 1 screen with a green background. So how we use SetColor. We're going to do it just like a regular basic or action SetColor. So we're going to do set background color. We're going to call it that. And the background color for graphics 1 is color register 4. So I want to get the color register 4, so I'm going to load the X register with 4, as I said before. Then I think it was, if you remember the basic program, the action program, my thing was 4, 12, 15. So we're going to load in the 12 first. Store that at hue. And then 15. That's going to be our luminance. Then we're going to, now I could go right to setting the colors here, but because I want to do, the next thing I want to do after set the background color is to set the character color. I want to make the set color routine a subroutine. So we're going to call this set color. And I'm going to start that at 1000 so I have some room. That's going to be set color. So how set color works is if I have, let's say my set color was 4, 12, 15. You multiply the hue by 16 and add the luminance and store that in the color register. So how do we do that? So what we're going to do is load in the hue. I'm sorry. And now we have to multiply that by 16. How do we multiply something by 16? We basically take, this is only in the low byte, right? It's 12, it's 8400. What we want to do is shift all the bits left so that the bits that are in the low bit of this are now in the high bit. So if you remember, we have this, we have the arithmetic shift left. And if we do that 4 times, it's like multiplying it by 16. So what that means is I started with this, and then after I shift the bits 4 places to the left, it looks like this now. Because remember, arithmetic shift left, as I go left, it puts zeros on the trailing end. So it doesn't rotate around like rotate left would. And even if it did, these are all zeros anyway. So that's what's going to be there afterwards. And now I know this is a place where almost all assembly tutorials start, but now it's down to the last video here before I'm finally going to teach you how to do addition in assembly language. So what we need to do is whenever you're going to do addition in assembly language, you have to make sure the carry flag is cleared. That's this. Clear the carry flag. Now I want to do add with carry the luminance value. So the accumulator had 12 in it, but now those all shifted left, and I'm going to add these into the right bit. And then I'm going to take that combined number and store that at color 0, but using the X index, which is color 4. And that's my subroutine. And here, after we've done the set color to change the color, then we're going to jump to our infinite loop. All right, so this controls our program start and end. This is the color register. We're putting in the color. We're not using this in this video yet. This is holding our hue and luminance. These are the equates we need to call the operating system IOCB subroutine. These are the values that we need here. We're doing open and close tonight. We're going to close the channel 6 screen and use the subroutine to do it. Then we're going to open by putting the screen name into the buffer and the open command into here, and set these auxiliary bytes, this for read write and this for graphics 1. Call that subroutine. Then we're going to do our background color. We're going to have X for color register 4, a hue of 12, a luminance of 15. Jump to the set color where we're going to stick that in there and then come back and then jump to infinity. So first thing I'm going to do, save this. Then I am going to assemble this. And the address for begin, you know, when you do these assembly listings, it puts all these equates and your labels in alphabetical order. So the course of the one that says begin is at the top and scroll off the screen. So let me just grab that begin. $4,006, that's begin. All right, ready? Let's see if this works and it doesn't crash the computer. And we're just saying go 4006. If all goes well, we're going to see a green graphics 1 screen. Well, I guess I got my colors wrong, but we're still a graphics 1 screen with at least a color. Did I get 4, 12? All right. And pushing the start or the joystick trigger should exit me out back into DDT. It does. Let's take a look at what I got wrong there. Four, 12, 15. Maybe it wasn't 12. Maybe it was some other color register. But anyway, you can, man. Oh, I see what I did wrong. Sorry. Maybe this messed it up. This should be arithmetic shift A. So it's probably using the wrong value there. It wouldn't be one of my videos if I didn't have a mistake. But that's how you debug. All right. All right, let's try this. What I wanted to do was arithmetic shift the value in the accumulator, not the value in hue. So that was my problem, I bet. Ta-da! Green screen. That's what I wanted. So that was my mistake. I was arithmetic shifting the wrong value. I wanted to arithmetic shift the right. So, and out. All right, so we covered basically the same things I covered in the last video. We covered how to use the how to be careful using the stack as a storage for temporary values. We covered how to use the bit command. We learned how to use the exclusive OR and the OR operators. We'll probably use those again in actual things. We created a graphics 1 screen in assembly language using the Atari's input-output control block, central input-output vector, subroutine, and we learned how to do SetColor. So that's a wrap for this video. And wow, I think I got this right to the minute, as long as the last video was. So thanks, and I am not going to delete this one, trust me.